Hello everyone. Today we are going to introduce 5G, a tutorial overview of standards, trials, challenges, deployment, and practice. My name is Penchen Xu and my team member is Maojun Xu. So we are going to introduce about the three parts: introduction, key technologies for RF interface for 5G, and then trials and test bands and deployment challenges. So first we'll answer the question, what is 5G? 5G is the fifth generation technology standard for broadband cellular networks. So it's a new set of wireless technologies that promise blazingly fast data connections to your phone. And you can get download speeds of over 1 gigabit per second, which is 20 to 30 times faster than a typical 4G LTE. And in IMC 2020, it is envisaged to support a diverse variety of usage scenarios. So for first, enhanced mobile broadband, the use case is mainly about hotspot. And for ultra reliable and low latency communications, we usually use it in the intelligent transportation system or V2X system. While in the massive machine type communications, the third type deployment could consist of a very large number of devices with relatively low or relatively high volume of non-delay sensitive data. Introduction is like this, and we are going to introduce about the key technologies for RF interface of 5G. So first key technology is increased bandwidth. So mobile systems today are widely deployed in the microwave bands, less than 6 gigahertz, and the bulk of the deployments use frequencies below 3 gigahertz. This spectrum is hugely congested. While in contrast, there is plenty of spectrum available in the centimeter and millimeter wave bands, like 28 to 300 gigahertz bands, and wide carrier bandwidths of order of 1 gigahertz are possible. And second key technology of RF interface 5G is massive MIMO. So what is MIMO? It is multiple inputs, multiple outputs. So basically, for example, it's an antenna, 2T2R antenna, which can do 2 times 2 MIMO. It has a low capacity, while if we increase the number of it, for example, the 16T, 16R massive MIMO antenna will have a much higher capacity. While the third technology is network densification. So its basic idea is to design a smaller cell for the tower, and so that it will result in traffic offloading to smaller cells, especially for indoor hotspots and dense urban microcells. So it has some benefits. And the last technology I'd like to introduce about new waveforms, or especially beam forming. So what is beam forming? We can see from the right picture that if we combine two antenna waves together, signals together, we can get some direction specifically strengthened, enhanced, like in the green direction. While in the blue direction, the waves get cancelled. So we can get a much stronger signal in specific direction using this technique. So it's just like a laser, and it can create a direct signal. The range of it is smaller and it can directly point to your phone. So with this technology, it will have less interference and less energy consumption. Then we'll discuss about the channel characteristics. The performance of 5G system is ultimately limited by the propagation channels they operate in. It is thus vital to investigate the channel characteristics are relevant for 5G system. In particular, those haven't already been explored for earlier generation system. In this case, we will mainly discuss millimeter wave channels and some measurements. So outdoor to indoor penetration is very important because a large number of cellular users are located indoors, and coverage by outdoor base stations will be a major goal for 5G system. However, the penetration through windows and houses was more attenuated at higher frequencies. The actual values of attenuation strongly depend on the material. While the post and drywall, the volume have less than 10 dB attenuation, the steel concrete of brick buildings in combination with energy-saving windows can impose 20 to 40 dB loss. So after that, we'll discuss about signal processing technique for 5G. So as we all know, the 5G technology is highly diverse. So clearly, there is no single approach will handle such disparate needs and elements of 5G signal processing. So this displays three kinds of beamforming: digital, analog, and hybrid beamforming. Consider K users with channel H1 to HK, and there's NS streams of data sent to a total NR receive antennas at the K devices. And the transmitter has NT antennas and forms the precoded signal S equals Fx. So different antennas will have different functions. Then we will briefly discuss about antenna layouts. So it's important to design the antenna layout to guarantee minimum receive signal levels for massive MIMO in a sense of aggressive spatial multiplexing with no explicit beamforming assumed. The antenna metric is a bit more involved. While for beamforming solutions, antenna elements in an array must be placed close together. So then we'll discuss about 5G new waveforms and channel access. So these are some parameters for 5G air interface. And this is a table of the difference of 5G per trio and LTE. You can see that for specific parameters, their difference vary apparently, while some parameters are the same. Then I will discuss about summary of waveforms for 5G air interface. There are pros and cons for each method, each scheme. So there is no free lunch here. We get something, we also lose something. And in general, there is no showstopper for the 5G use cases and scenarios. So then my teammates will continue the presentation.
The seventh part is trials and test beds. Even though 5G standardization is still at an early stage, 5G prototypes, test beds, and experimental technology trials have been in progress for many years, developed by universities and operators. Massive MIMO, model vendor are most common targets of test beds. Testbeds for massive MIMO below 6 GHz have been developed and have successfully demonstrated that it is possible to achieve the gains predicted in many theoretical studies in real-time and real-life scenarios. Universities of Bristol and non-universities firstly implemented massive MIMO testbed, which shows that huge gains in spectral efficiency are achievable in real-time and over-the-air trials. Researchers achieved a record-breaking spectral efficiency of 145.6 bits per Hz, with 128 antennas at the base station and 22 single-antenna mobile stations over a 20 MHz radio channel. However, a few outstanding problems still yet to be solved include the following. For the mobility, where massive MIMO works under rapidly changing channel conditions as the mobile terminals move at high speed. And for the FDD, if TDM mode of massive MIMO will receive widespread adoption. And for the multi-cell operation and cell edge performance, will massive MIMO still work when users are located at the edge of agency cells? And also there are many other open areas, such as distributed massive MIMO. The seventh part is trials and test beds. Even though 5G standardization is still at an early stage, 5G prototypes, test beds, and experimental technology trials have been in progress for many years, developed by universities and operators. Massive MIMO, multi vendor are most common targets of test beds. Currently, most test beds operate using an isolated facility model. This means a single entity owns and operates its own test bed. A federated test bed is a system that allows each individual test bed to maintain its own autonomy. We are working with others to share technological resources. The challenge is to design a system that respects the intellectual property and autonomy of each side, while balancing the need to share resources to optimize technologies. For example, the UK government announced six primary test beds that would receive the first round of funding. These test beds focus on the field of hard-to-reach remote areas, the visitor experience at museums, the robotics, and autonomous vehicles. Almost all major infrastructure providers, such as Huawei, Samsung, Qualcomm, and Intel, have reported and showcased trials with many antenna systems. Multi-vendor trials have been announced by the China IMT 2020 Promotion Group, CMCC, DOCOMO, and before 2020, the main problem shows that none achieved a single user peak rate of 20 Gbit per second. And with the continuous development of the 5G technology, many problems reflected in the trials have been resolved, and people began to think about how to further play the role of test beds in innovation. For part of deployment challenges for 5G, as we know, 5G has been touted as a game changer with lightning quick speed and lower latency. So the only question is, how do we make this happen? The answers are not so simple. The first problem we should consider is the coverage holes. NR will be deployed in both microwave bands and higher frequency bands. However, if 5G is deployed on exiting 4G site, there is likely to be many coverage holes as the intersite distance on these frequencies is much smaller than the present intersite distance. Also, the choice of single and multi-stream transmission, the convoluted architecture, the channel measurements, and the security concerns. These are all big challenges waiting for us to resolve. This is our presentation. Thank you for your listening.